Okay, welcome back. We're going to proceed on with the central force problem in Lagrangian mechanics, and this will be a prelude to the central force problem in Hamiltonian mechanics. And this is all a prelude to understanding how it compares to the general relativistic treatment, which we've begun already. And this is basically a classical mechanics interlude in our study of general relativity. I'm trying to go back and review these very critical concepts of the classical theory of mechanics, which is very valuable. I mean, it's a really, really good idea to get back and start applying these things again. And we're only going to do some elementary work anyway. But this was the Lagrangian of the central force problem. This is the one we actually talked about. But understand that you can do the central force problem entirely in two dimensions, in which case the Lagrangian would look like this. We're actually going to do it in the full three-dimensional form. I think that's just a little more edifying. And our standard was that this was a central potential, which by definition means it only depends on the coordinate r in a spherical symmetric system. And just so we have it real clear, our spherical symmetric system is going to look like this. I suppose we could say that's z, x, and y axis, but the coordinates we're dealing with will be, let's see if we have a vector out here. The vector will have a length r, an angle off of the vertical axis theta, and then a projection. The azimuthal. This will be the polar angle. We'll call that the polar angle. And then this angle here will be that angle there. The azimuthal angle will be phi. That's called the azimuthal angle. I don't know if those are absolutely universal phrases, but you can actually see how this sine theta would be, this sine theta, in order to get a velocity with respect to a change in the azimuthal angle, you're talking about the sweep of this projection of the overall vector we're dealing with, and that projection, of course, is going to introduce this sine theta term, which would be which reflects the projection of this on this xy plane, the projection of this vector on the xy plane. So that's where this sine theta term comes in. But what's critical here to note is that, of course, that there is no dependence on the azimuthal angle. There's a dependence on theta through this term, so the coordinate theta is part of this problem, and the coordinate r is part of this problem. But the azimuthal angle only shows up as its derivative, and we remember that the Lagrangian is a function of r, theta, phi, r dot, theta dot, and phi dot, and we treat these as independent variables. That confuses people a lot because it seems like, well, r dot really should depend on r. But not necessarily. There's no reason to think that the rate of change of r for some particle in our system should depend on where it is. I mean, ultimately, the two could be linked, but it doesn't necessarily have to be that way. There's maybe a constraint that forces them to be related, but it doesn't have to be that way. So we treat these things as independent variables. And that's real important because in the Hamiltonian formalism, this will all change, and this will become r, theta, phi, momentum, conjugate momentum of r, conjugate momentum of theta, conjugate momentum of phi. And again, those are all also completely considered to be entirely independent quantities. All right, so in the last lecture, we basically showed how we were going to handle the analysis of a system that's described by a Lagrangian. And right now, this represents the kinetic energy portion of the Lagrangian, and this is the potential energy portion. The force is central, but we haven't specified the force, but it is central. We will specify it at the end, or we'll do some development in general, in full generality, and then we'll specify the usual inverse square law potential. And when I say inverse square law, I mean that the force obeys an inverse square law, but the force is the gradient of the potential. So the potential itself, so U is going to end up being proportional to 1 over r. And that'll give us a force that's related to, that's going to go as 1 over r squared. So the potential will end up being 1 over r. Okay, so let's begin. So we'll begin with this Lagrangian, and we'll start with the first of Lagrange's equations, which is, we'll just go with the radial one first. And these derivatives are not at all difficult, focusing on the fact that when you take this derivative, you're treating this generalized velocity as an independent coordinate. And here we have the derivative. This first derivative is this piece right here, where we notice that this comes in as minus the potential's derivative with respect to r, and this derivative with respect to r dot, showing that we're treating r as independent, r dot as an independent variable, so it's just mu r. Mu, by the way, is the reduced mass of this two-body system. Something from elementary physics is to calculate the reduced mass. You can treat this two-mass system as though it's one mass, and so that derivative is just 2 times r dot, which cancels with this, which leaves mu, so it's the derivative of that with respect to time, which is going to end up being minus mu r double dot. And here it is all written out where we make the leading term positive, right? So we change the sign of things. And this expression here, this is often preferred to be written this way, equals the force, the generalized force in the r direction, right? Because when this goes to the other side, you get minus partial u partial r, which is the definition of the force. It's the gradient of the potential, and there's only one component to that gradient, and that's the radial component, because the gradient is only a function of r, right? It doesn't, the potential is only a function of r, so the gradient's only a function of r, so the force is only a function of r. So that is our radial equation. Now we have 2 other equations to solve for. The theta equation, the polar angle equation from exactly the same Lagrangian, the Lagrange equation expressed in terms of the polar angle is right there, where now we treat the generalized velocity of the polar angle as an independent coordinate. And this derivative here is just this guy, because the only place where the polar angle appears explicitly is right there, right in this sine squared theta. So that becomes mu r squared sine squared cosine, sine theta cosine theta phi dot squared. And then you have the full derivative with respect to time of the partial derivative of the Lagrangian with respect to the generalized velocity of the polar angle, which exists in this term. So that becomes the 2's cancel, and you get mu r squared theta dot. So this derivative we have to take. But this is a full-time derivative, and r is a function of time, and theta dot is a function of time. So understanding that r is a function of time and theta dot is a function of time, we have to proceed carefully with that derivative, leaving us with this term here. It's minus. Yes, that's right. So this is our theta coordinate, theta constant of motion, which we can rewrite very easily. And this is kind of a mess, right? This is just understand, it's a couple differential equation for theta that involves r, and r is an unknown guy who's dependent on this, also coupled through theta dot and phi dot. Of course, phi dot's in here as well, theta dot's in here. These two, this equation here and this equation here, have to be simultaneously satisfied. Notice the potential, of course, doesn't show up in any of these other expressions because it's only a function of r, and through Lagrange's equations, everything's a derivative with respect to these various independent variables. So unless one of those two is r, this guy's never going to show up. This potential is never going to show up. Now the last equation is for the azimuthal coordinate, phi. And we just the same thing. We start with the same Lagrangian. We execute the same Lagrange equation. This is the third and final Lagrange equation carrying the generalized coordinate phi and the generalized velocity phi dot. Now, what's very important and famously important about this is that the Lagrangian does not have phi as an explicit variable, an independent variable. It's actually independent of phi. And this is very important because that means this first derivative term goes away, leaving the second derivative term to deal with. So we can take the partial derivative of the Lagrangian with respect to phi dot easily enough, and we get this result here, mu r squared sine squared theta phi dot. And we could take the derivative with respect to time, and if we began that enterprise, we would end up with minus 2 mu r dot sine squared theta phi dot plus mu r squared, 2 mu r squared sine theta, 2 mu r squared, let's see, what would it have been? Yeah, sine theta cosine theta dot phi dot minus mu r squared sine squared theta phi double dot, right, equals 0. So, and that would be totally true, but it would complicate things because we want to exploit the fact that we have the full-time derivative of something equals 0, right? That means that whatever that something is constant, right? So we can definitely now write mu r squared sine squared theta phi dot equals some constant which we're going to call h. And the critical part is we can now invert this, well, not really invert it, but solve it for phi dot and get h over mu r squared sine squared theta. And this h, that guy there, let me do that in red. That guy there is called a constant of the motion. And it's a constant of the motion because phi is cyclic. And cyclic is defined as, cyclic is defined as this term here equals 0. The Lagrangian is independent of that particular coordinate. And so this expression looms very large in the rest of the analysis because now we can use that fact. Now notice this is not constant. Phi dot is not constant. Phi dot is dependent on time because theta is dependent on time and r is dependent on time. What's a constant of the motion is this complete expression. So no matter however r depends on time, the sine squared of theta is going to exactly compensate in such a way that the rate of change of the phi coordinate is going to equal this expression right here. And this constant h now becomes something that's established by the initial conditions of the problem. And so there we kind of have our three equations of motion. These are called the equations of motion. They're probably not in the simplest or cleanest form as I've got them right here. You know, usually we would like the second derivative term to have to be all alone, so it would be phi dot. I could divide everything by r squared. You know, I could divide everything here by mu, and also what's critical here, of course, is that everywhere I see a phi dot, I can substitute this, and I eliminate the phi dot squared. So the phi dot squared here and here can be eliminated in favor of this constant of the motion and some more complication involving these variables. Although it's not clear to be a complication, right? If I put this in here, well, no, it would be, right? So, and we'll do that in a moment, actually. But I just want to make it clear that this is the goal. Getting these equations of the motion is the goal, and presumably there are the answer to this problem is phi of t, or theta of t, phi of t, and r of t. And those, that'll give you the complete story of how this system, your system is configured in time. You give it a time, it tells you the coordinates. It tells you all three coordinates. It's very much like the world line we discussed. And when we talked about a world line through space-time, we were saying, hey, I have some parameter lambda along the line, and I want to know what time it arrives at lambda, what's its x-coordinate for lambda, what's its y-coordinate for this parameter lambda, and what's its z-coordinate for this parameter lambda. In classical mechanics, the parameter lambda, which is the sort of position or this parameter that parameterizes a world line, is, in classical mechanics, that parameter is played by the role t in 3 spatial dimensions. In general relativity, we have 4 dimensions where time actually becomes one of the coordinates, and now we need a new parameter to sort of measure our progress along the world line. In this case, the world line is just a map in space. So, although you could add time as a dimension, that would be fine. It would be like a parametric set of... It's a parametric set of equations in both cases. But here time acts as the parameter, and here lambda acts as a parameter, and time is just one of the equations, one of the parametric equations. Now, eventually in general relativity, this parameter becomes another form of time. It becomes the proper time. But understanding this parallel is really important, and with the Lagrangian formulation, you really get a sense of time is just purely a parameter. By the way, time could be part of the Lagrangian. You could have a time-dependent Lagrangian. The potential could be a function of time, or time could explicitly show up in here, and there's reasons why it might. I think I brought them up in the last lecture. But in our case, in the central force problem, we're assuming that the only thing that might depend on time is the potential. It could still be a central force problem with a potential varying on time with time. It just wouldn't be the one we're solving. We're solving a constant central force problem. All right, so now it's time for those simplifying assumptions, very similar to the ones we did in the previous analysis of the Schwarzschild geometry. So in this case, the simplifying assumptions we're going to deal with, let's see. If we imagine our coordinate system, which has got to be arbitrary, right? Our coordinate system is sort of just set up. I always like to put the x, y, and z here. And we could imagine, for example, because of the way the forces work, the forces are always in the radial direction. And from this, we could say, therefore, the forces in the theta direction and the forces in the phi direction are both 0, right? And if that's the case, there's no way an orbit can change from one plane to another. So once a body is established to be working or moving in a certain plane, it must stay in that plane, right? So we can sort of propose that this orbit here, it would be in the theta equals pi over 2 plane, and it'll never leave. Now we could also presume that theta is in the, let's say, in this plane, right, where it is in the zy plane, in which case we have theta equals well, actually, in this case we have not theta equals something. We have phi, right? The azimuthal angle is constant, and it's, I guess the way I drew it here, it's 0, right? So there's these two possibilities certainly exist. The idea, if you're going to do a hand-waving argument would say, oh, well, let's just take theta equal pi over 2, and theta dot is a constant, and or theta dot is actually 0. I'm sorry, not a constant. It's 0, right? It doesn't leave the plane. And likewise, we could say phi equals 0 and phi dot equals 0. And if we did that and we went into these equations, what would happen? Well, the first thing that would happen is this would be 0, right? And this term would be 0 because theta is pi over 2 and cosine of pi over 2 is 0. And then this term here is sine of pi over 2, which is 1, so that goes away. And then we're using the theta equals pi over 2 theta dot equals 0. And then, well, theta dot is 0, so theta double dot is 0. And so we are left with, oh, and then we substitute out for this guy, right? We substitute out for this guy using this expression here. And we get a pretty radically simplified problem. We get 2 mu r dot minus r minus mu r squared cosine theta over 2, so that's going to be, wait, no, that one went to 0, right? That one went to 0. So, oh yeah, so this whole equation goes away, right? Everything's 0. So this is just 0 equals 0. That's nice. Of course it had to be that way. I don't know why I was puzzling over it for a moment. Then this one here, this one better not go away. So in this case, though this term does go away, and this here becomes 1, and then we substitute in for that. So we get mu r double dot minus mu r, and then this becomes h squared over mu squared r to the fourth, because this sine squared is now equal to 1, right? Plus partial u partial r equals 0. And so that ends up with mu r double dot minus h squared over mu r to the third equals partial u partial r, which it's important to write this as r double dot, mu r double dot equals partial u partial r plus h squared over mu r cubed, right? So that's what would happen if we made that particular simplifying assumption. Wait, there's a minus sign missing. There needs to be a minus sign here, and so that needs to be a minus sign. That's still a plus sign. Okay. Now what's evident from this is the significance of two critical observations. Of course, this was critical to simplify this problem. We did use a little bit of a hand-waving argument to get there. In other words, we concluded because these forces in these theta and phi direction have to be 0, there can be no motion outside of a single plane of motion. Therefore, if we set the initial condition such as this, with theta is pi over 2, we automatically know that it's going to stay in that position, or stay in that plane. And because of that, we are able to radically, we eliminated an entire equation of the motion, which essentially is telling us that all of the geometry could be expressed two-dimensionally. And if we started with a two-dimensional problem, this reduces to a two-dimensional problem is essentially what that says. And that's exemplified, that's demonstrated by the fact that one entire equation of motion just goes away for the properly selected coordinate system. All right, so now that we've seen that, we can kind of reduce this whole problem down to two dimensions. And the hand-waving argument that establishes this idea is actually very well grounded. We can do that analysis completely thoroughly by asserting that, for example, I think we can assert that if the motion ever goes through theta equals 0, it's going to stay there. And we can use the constant of the motion to make that claim. Maybe we should just do it. Hold on. the way we show this formally, so we're not waving our hands through this, is that the angular momentum, the square of the angular momentum is r cross p squared. Well, now I'm going into classic standard physics vector notation. So this is a regular cross product, r cross p squared. And that can be reduced to the magnitude of r squared p squared minus r cross p, r dot p. Notice this is all real numbers. So this is a vector. I guess I should make L be a vector here too. If I had boldface, it would be obvious. So L is a vector. So these are all real numbers. Real number, real number, real number, real number. All right, so this can be reduced as such, right? So r cross p, so this part, r squared p squared, if you just peel that apart, that's 2 mu times the kinetic energy times r squared. So this p squared is 2 mu times the kinetic energy of the motion of the particle, and then r dot p. Well, p is mu r dot, and r is r, so it's this term squared. And this is so this was the angular momentum of our particle, right? I guess the way to think about it is, okay, the kinetic energy is p squared over 2 mu, right? That explains that. And this is the projection of the momentum in the r direction, which is simply this. Okay. So the next step is just to substitute for everything we can. R squared is this, and that comes from the equation of motion here, right? This equation of motion, you solve it for r squared, and you get h over mu sine squared theta phi dot, if you put r squared over here. So that's this substitution, right? So this is r squared right in here. And this is the kinetic energy right here, right? That's the kinetic energy, so that's K, and there's the 2 mu. So the 2 mu, the K, and the R squared, they're all accounted for. Then this part here is R squared. This part's R squared, this is mu, something's missing, yes, the R dot, right? Yeah, there's this r dot right here squared is missing. So I got to put that r dot squared. Okay, so that's L squared. And I guess I should have substituted for these two r squareds also, right? Here's an r squared right there. I should have substituted for those two as well. Let me do that. Okay, so here I've put them back in. I put this r squared here is now this, and this r squared here is the same thing, and there's that one and there's that one. So there's a lot of obvious cancellations here. The most important being this 2 mu, the 2 cancels with this 2, this becomes a mu squared. The mu squared multiplies this r squared, so I have this factor, mu squared r squared, but that's this factor, mu squared r squared. So what's nice is this term here, well, this term here cancels with this term here. So that was a good simplification. And now everything else has this term leading it, right? Well, this term squared, right? That term squared leads that and leads that. The first term, that means this guy here, is going to be an h. This h and this h give me an h squared. The sine squared and the sine squared give me a sine to the 4th power. Then I get mu squared. This mu here and this mu here give me this mu squared. And then that phi dot and that phi dot give me phi dot squared. This mu and this mu give me mu squared. And then there's theta dot squared. So that's all good with the obvious problem, and that should cancel. And then that leaves us with this term to handle. But this term is going to massively simplify because you have a phi dot squared in the numerator, phi dot here and a phi dot here, so the phi dots completely go away. This sine squared cancels with that sine squared. This mu cancels with this mu. And then this mu cancels with this mu, so all that's left from that one should be h over sine squared theta. Is it that simple? Really? Let me just double check. Well, it's h squared for sure. H squared over sine squared theta. All the mu's cancel. I have 2 mu up, 2 mu down. Yeah, so that's that. So so now I guess this thing is, and that's what that simplifies to. And then we make whenever you see this, we know we got to get rid of that because there's a constant of the motion that defines it. We've already used the constant of the motion once, so putting it back in means we're kind of undoing a substitution we made earlier. But because we've done so much simplifications, we're not literally going backwards. We're probably legitimately simplifying one term. I always get nervous when I substitute twice and inverted. I feel like I'm just making no progress. But in this case, we actually are. So this becomes h over mu squared sine squared theta r squared, right? It's now this original constant of the motion expression here, this one, as is. So it's just the square. So it's everything squared. And so I got to square that. Whoops. I've got to square that. And then that'll be theta dot squared plus h squared over sine squared theta. And then what happens here is everything, again, kind of uncancels itself, or cancels itself out, I suppose. So that's going to be something's wrong. Oh yeah, this mu is not mu squared. It's just mu. It's just mu. If you go back here, it's just mu. It's not mu squared. So the things will cancel. So the h's will cancel. Let me make sure the h's will cancel. The signs, the factors will cancel. But then you'll end up with mu squared r to the fourth theta dot squared plus h squared cosecant squared theta. All right, so that is the value of the angular momentum of this system. And that's going to be a constant, right? Spherical symmetry, angular momentum will be constant. So this number here is not going to change with time. So as time marches on, r will change, theta dot will change, but this angular momentum will always be the same. Now, by the way, an important and interesting fact is that the associated canonical momentum, which is given by the derivative of the Lagrangian with respect to the coordinate, right? In this case, for the theta variable, that value is going to be mu r squared theta dot. Right? If you take the derivative of the Lagrangian with respect to theta, you get mu r squared theta dot. So that is, so we can write this as p theta squared plus h squared cosecant squared of theta. In case that's just an important thing. It's always good, even if you're dealing just in purely the Lagrangian formalism, it's always good to write down the canonical momentum. It's something that you'll need to transition to the Hamiltonian formalism if you're interested in, and also it's just to remind you that that's the definition of the canonical momentum. It's the partial derivative of the Lagrangian with the associated generalized momentum. Okay, so this is the constant that equals L. Now you'll notice I pulled a little bit of a fast one. I said, oh, L, we know L is constant, but that's the whole point. We're supposed to be figuring out L is constant, right? We know that the angular momentum of a spherically symmetric system is constant, but the goal is to figure that out. So how do we figure that out? Well, we want to calculate dL dt, the total time derivative of the angular momentum of the angular momentum, actually dl squared, right? Because that's the real number. The total time derivative of the square of the angular momentum with respect to time. That's what we want to calculate to prove, and when we want that to be zero, that better be zero, because we are expecting that the total angular momentum will be zero. So we calculate this derivative explicitly now that we know what this is. So the time derivative of L squared with respect to the derivative of L squared with respect to time is going to come out to be 2p theta p dot theta. H is a constant. The derivative of cosecant squared is cosecant squared cotangent. This is always a good time to review. I like to, whenever I run across, the derivative of cosecant squared, I don't remember it. I like to work it out. I don't like to just look it up. I keep a Calculus 2 book with me, just a classic, basic, Calculus 1, 2, 3. And I go to the integral section or the derivatives, and I see how the derivative is actually taken. Although it's not hard to take these derivatives. Integrals is much more of a challenge, and you spend a little more time in that calculus book studying integrals. But anyway, this is the derivative of that with respect to time, and that had better be equal to 0. Whoops, I just realized something. This definition, I kind of screwed this up. There's a dot here, right? That's the definition of the canonical momentum. Without that dot, this is not the right derivative without that dot, right? We're taking the derivative with respect to theta dot to get the canonical momentum associated with the theta direction. So that dot's there. And the reason that I was suddenly reminded of it is I saw this dot here, and it just triggered that I didn't include the theta dot in its definition. Because the next step is going to be to show that this guy, in fact, equals 0. And we do this by retreating to the Lagrange, or to the Euler-Lagrange equation for the theta direction. We write down the following thing. We write down, this is Lagrange equation, which we know is satisfied, right? We know that whatever theta of t is and theta phi of t is with this Lagrangian, this is a true equation. It's the physical path. It represents the criterion for the physical path to be the true path, or for the path theta of t to be the true representation of the path in space. It all goes back to Hamilton's principle. So this is true. Obviously, it's true, but the point is you can lean on this to be true because it defines the motion. It's the physical. It's really the axiom. It's the basic axiom of our whole theory of mechanics. I know, in a way. I guess not even in a way. Literally, you could argue that mechanics is based on the hypothesis that this equation is always true for the actual motions in space-time, or in space. So, but this is equal to the canonical momentum, right? This part of the Euler-Lagrange equation actually is the canonical momentum. So I write it this way. Now I can write it as the time derivative of the canonical momentum equals the partial derivative of the Lagrangian with respect to the associated generalized coordinate, which in this case is theta. So I get this expression, which, to complete that equal sign, is mu r squared sine theta cosine theta phi dot squared. And so what I'm ultimately trying to do is I'm trying to recreate this statement based on the Euler-Lagrange equation. I'm going to recreate this from a different angle. Now I know what p theta dot is. It's equal to this thing. So what is p theta dot? So p theta dot, that guy is going to equal mu r squared, theta dot times mu r squared sine theta cosine theta phi dot squared, right? That's what this first factor is equal to. It's equal to this thing. And now, as ever, we look at this and we make the substitution from the constant of the motion. And this is that. This is that substitution for phi dot squared using the constant of the motion from the Lagrange equation for phi. Basically, we're redoing the Euler-Lagrange equation for phi, which was cyclic and gave us this constant of the motion, the relationship between phi dot, the constant of the motion, which is this relationship right here. We've used that so many times. You see how important these constants of the motions can be. In this case, it's the same one over and over again, but this is totally typical in these problems with cyclic coordinates. It's having these constants of the motion allows for all this simplification. So anyway, then you take this guy and you simplify everything that's left, and you get, we kind of break up this sign to the fourth. You use 1 to cancel with this, leaving 2 in the denominator, and then leaving 2 in the denominator with 1 left over, which you put under the cosine, so it looks like cotangent, cosecant squared, h squared, theta dot. So now you know that p theta dot equals this expression, and dl squared equals this expression. And okay, so why don't they cancel? So this is obviously this, when I substitute in here, supposed to make all this cancel, proving that dl dt is 0. But it's not going to cancel. It's going to add, and there's this weird factor of 2. And of course, if I go back, I can immediately find my mistake. I can almost see it now. This is correct. But this derivative, this cosecant derivative that I was so proud of, well, it's all wrong, right? It's minus 2, right? I forgot to take this 2 out, and it's a minus sign. There's a minus sign in that derivative. So this is the correct expression. And so now, when you substitute this into here, it gets 0. And now you know that the total angular momentum, the change in the total angular momentum is 0. Okay, so that at least tells you now that once it's in a plane of motion, it's always going to stay in that plane of motion. We actually proved that point. We've actually proved that total angular momentum is 0 using this sort of long classical argument. Always worth doing, always worth doing. So now that we've convinced ourselves that the angular momentum is constant and we know that all motion is in one plane, we can go ahead and lean on this idea that theta is pi over 2 always, with theta dot equaling 0, and make that substitution like we did earlier into these expressions and sort of get our final choice of these equations of motion. And here they are, right? It'll be these two. The first equation of motion is just the constant of the motion term, which now reduces to something very elegant because this sine theta part is now just 1. Then this term goes away, that becomes 1. We use the constant of motion to replace this, and we end up with this nice little expression. This is a force, right? A mass times an acceleration, so this needs to be a force, and we know this is a force because the definition of the force is it's the gradient of the potential, the minus the gradient of the potential. So this is a force and this is a force. This is a force that's only dependent on the radius, so it's very, very tempting to write this minus mu partial of dr of u, and then plus h squared over mu r cubed, right? And this term here can actually, so this is the actual potential. This is the physical potential that exists because of the central force, right? Somehow there's a potential field out there that produces this central force. But there's this other force that depends on the cube of the radius that also exists. And it would be interesting if, since that's a force, we can ask the question, hey, is this force here, could it be that h squared over mu r cubed, could that be the gradient of some other potential, v, call it? And if so, we could create a new potential, u plus v, right? And the overall force is going to be the minus gradient of this u plus v. And sure, this is completely possible. In this case, V would just be, let's see, that value would be, if V is h squared over 2 mu r squared, if you take the partial derivative of V with respect to r, which, you know, in principle, there's no other real variable here. I mean, this is a constant, and the mass is a constant, 2 is a constant. Although you could ask questions about how V changes with respect to the changing of the angular momentum. But that aside, this partial derivative is going to be minus 2 times h squared over 2 mu to the r to the minus third power. And the 2's will cancel, leaving minus h squared over mu r squared. And the force is the gradient of this, right? So, or the opposite of the gradient of that. So this becomes a plus. And so we can do that. We can now write mu r double dot is minus partial r of u plus h squared over 2 mu r squared. And this is our new potential, right? Again, this is the physical potential, the potential that was there at the start of the problem. And this is a potential that appears due to our choice of coordinate system, right? But it's still just a totally legit potential because all we're after is this differential equation here in the end. And so we call this guy here the effective potential, V effective. And it'll be very interesting to see how V effective is different in the Schwarzschild geometry as it is from this Newtonian geometry. Now, we haven't really poured into the full Newtonian problem yet because we still haven't substituted for you the basic Newtonian potential that's proportional to 1 over r. And we'll do that next time. Okay, so what have we done? We've taken the full three-dimensional Lagrangian, and I pulled no punches. Normally you don't see this full analysis. You don't see, there's this assumption, this hand-waving assumption that you can guarantee that the motion will stay in the plane, but we decided to actually painfully calculate that. And even though, barring my screwed-up derivative, we were able to show that the angular momentum with respect to time is in fact 0, and that is a consequence of Lagrange's equations of motion. And once we showed that, we chose arbitrarily this particular plane of motion, where theta is pi over 2, and theta dot is going to be 0 by this discovery, by this discovery that the angular momentum doesn't change, or that all the plane of motion stays the same. And we took the Lagrange equations of motions, simplified the heck out of them, discovered the constant of the motion, simplified this equation, took this equation and made it a simple equation for the acceleration in the radial direction as a function of, or acceleration of the radial direction and driven by the effective potential, which is the physical potential plus this geometric part of the potential, which is every bit just as legit as far as being a potential goes. And so when we solve this, we will ultimately solve this to get r of time. So we always know the radius with respect to time. And once we know r of time, we put that in here, and we end up with phi. Well, we end up with a differential equation for phi dot, but r is eliminated, right? So this will be just a differential equation. R is a function of t. So this will be a differential equation with respect to independent variable time, which we integrate, right? We would integrate both sides, because this is now r of t dt, and we would end up with an equation for phi with respect to time. Phi with respect to time, r with respect to time, that's the answer to the problem. That is the solution to the problem. And because we know that theta with respect to time is a constant pi over 2. We've stipulated that. We know that's not going to change. So that's how you get to the answer to the central force problem. So what remains is to substitute for the particular central force we're interested in, and then complete the classical analysis of the Newtonian central force problem. So we'll do that next time.